Now I am going to start module 2 of chapter 3. In this module, we shall find or we shall discuss about the methods for solving a second order partial differential equation with constant coefficients. In the entire discussion, we shall be confined on taking two independent variables, and this process or method can be extended when there are nth order partial differential equation with constant coefficient. The entire module is divided into two sections. In the first section, I shall discuss how to find general solution of a homogeneous equation. Then in the next section, I shall discuss how to find particular integral of a non-homogeneous PDE with constant coefficient. So, let us start the first slide of this module. As I have told, in this module, I shall discuss about the solution of a linear partial differential equation with constant coefficient. The general form of a linear PDE with constant coefficient can be written in the form capital F d d dash z equals to f x y, which is written in equation number 1, where capital D is the partial derivative with respect to x and d dash denotes partial derivative with respect to y, and capital F is in the form sum over r, sum over s, c r s, d to the power r, d dash to the power s, where c r s are some constants. Now, we shall first discuss the general solution of the equation capital F d d dash z equals to 0, and the general solution of the equation which is written in equation number 3 is called the complementary function of the equation 1, and any particular solution of equation 1 is known as its particular integral. And there is a well known theorem which states that if u be the complementary function and z1 be a particular integral of the equation 1, then u plus z1 is a general solution of the given equation, that means equation number 1. And there is another theorem I need to state here, which is written here: if u1, u2, un be the n solutions of the linear homogeneous equation f d d dash z equals to 0, then linear combinations of these functions, that means sum of CR UR r equals to 1 to n, where CRs are constants, is also a solution of this equation, and this is called the superposition principle. So, for a linear equation one can apply superposition principle. So, now we shall categorize a linear differential operator f d d dash into two classes. One is the reducible and the another one is the irreducible form. The function f is said to be reducible if it can be written as the product of linear factors of the form alpha d plus beta d dash plus gamma, where alpha, beta, gamma are constants, and capital F the case B, where capital F is called irreducible if it cannot be factored into linear factors, as it is done in class A. Now, I am taking here one example where you can see one reducible factor and another irreducible factors. So, in this example, capital F is d cube minus d square d dash minus 2d d dash square. Now, if we factorize this F, we will get the factors d into d minus 2d into d plus d dash. So, in these factors you can see that all the factors are linear factors. So, this F is reducible, but if we take another F where capital F equals to d cube minus d square d dash into d dash plus 1 plus d dash minus d dash square minus d dash cube. If we factorize this F, we will get two factors which is written here, d square plus d dash and d minus d dash minus d dash square. If we observe these two factors are not further reducible to linear factors. So, this F is called irreducible. Now, I shall discuss the case where the function F can be factored into reducible factors. So, for that I need to state one theorem which states that if alpha r d plus beta r d dash plus gamma r be a factor of F and phi r xi is an arbitrary function of the single variable xi, and we also assume that alpha r is not equals to 0, then u r equals to exponential of minus gamma r by alpha r x into phi r beta r x minus alpha r y is a solution of the equation f z equals to 0. But if alpha r equals to 0, then the theorem is the next theorem which is stated here. For that case, we are assuming that beta r is not equals to 0. So, beta r d dash plus gamma r, if this is a factor of f and phi r xi is an arbitrary function of the single variable xi, then the solution is u r equals to exponential of minus gamma r by beta r y into phi r beta r x. So, using these two theorems, we can find the solution of a homogeneous equation. So, we to illustrate the idea, we are taking one example. So, capital F, the expression for capital F is written here, d cube plus 3d dash minus 4 into d square plus 3d dash square minus 8d plus 3d plus 3 in minus 4d dash plus d dash square into d dash z equals to 0. So, if we observe the function capital F, then we see that capital F can be factorized, which is given in the solution in this form, d plus d dash minus 1 into d plus d dash minus 3 into d plus d dash z equals to 0. So, for this example, f is reducible to linear factors. So, using the first theorem, the one solution is e to the power x into phi 1 y minus x and e to the power 3x into phi 2 y minus x, and the third solution phi 3 y minus x. Now, the linear combinations of these three solutions will give the general solution of the given equation, which is written here z equals to the sum of these three functions. Now, suppose that there is a linear factor of f, but that factor is repeated. So, let us take one example where the linear factor comes twice and it is written in equation number 4. So, to solve this equation, we assume another function, another variable z as alpha r d plus beta r d dash plus gamma r into z. So, if you assume the expression for capital Z like this, the equation 4 reduces to the form alpha r d plus beta r d dash plus gamma r operating on capital Z equals to 0. Now, Z is our unknown function. So, using the previous theorem, we can find the expression for Z as Z equals to exponential of minus gamma r by alpha r x into phi r beta r x minus alpha r y. We also assume that alpha r is not equals to 0. Now, if we see what is our capital Z, this capital Z we have assumed as alpha r d plus beta r d dash plus gamma r into Z. So, putting this value of capital Z, we obtain the equation alpha r del Z del x plus beta r del Z del y plus gamma r Z equals to some function of x and y, which is written in the right side. Now, this is a first order partial differential equation, and we know how to find solution of a first order differential equation. We have learned that in chapter 2. So, using that concept, one can find the corresponding auxiliary equation or Lagrange auxiliary equation is like that: dx by alpha r equals to dy by beta r equals to dz by, which is written here. Now, this simultaneous equation can be solved easily. So, if we take first two equation, we can get a solution beta r x minus alpha r y equals to constant. Let us say that constant is C1, and we can say there is one expression beta in the equation in the denominator of the last expression dz by some function. So, where beta r x minus alpha r y is present. So, in that place one can replace that function with the constant C1. So, putting that value, we obtained the relation which is written here. So, taking the first equation and last equation of the simultaneous equation, that means dx by alpha r equals to dz by minus gamma r z plus exponential of minus gamma r by alpha r x into phi r C1. Since C1 is a constant, this is a ordinary first order linear differential equation. So, one can solve this linear differential equation easily, and the solution is written here: z equals to 1 by alpha r phi r C1 x plus C2 into exponential of minus gamma r by alpha r into x. Now, to find the solution of the original equation, we need to replace C1 by the function beta r x minus alpha r y. So, replacing C1 and also the C2, the expression for C2, we can obtain the function z equals to x phi r beta r x minus alpha r y plus r beta r x minus alpha r y into exponential of minus gamma r by alpha r into x, where phi r and psi r are the arbitrary function. So, this idea can be generalized when there are n repeated roots in the function capital F. So, that theorem is stated now: if alpha r d plus beta r d dash plus gamma r to the power n be a factor of F and the functions phi r1, phi r2, phi rn are arbitrary, then a solution of the equation f z equals to 0 is z equals to exponential of minus gamma r by alpha r x into sum of a x to the power s minus 1 phi rs of beta r x minus alpha r y, and these phi r are the unknown functions. Since there are n reducible factors, so there are n unknown function or arbitrary function, and so the solution in the solution, the unknown functions are coming as sum of this function which is written here. Now, we are taking one example to illustrate the previous idea. So, in this equation, in this example, the equation is given d cube minus 4 d square d dash plus 4 d square z equals to 0. So, capital F can be factorized in this way, d into d minus 2 dash whole square z equals to 0. So, we can see that d minus 2d dash is a double root. So, we need to use the concept which we have learned just now to find the solution. So, one solution, the first one z equals to phi 0 minus y, this corresponds to the factor d, and there are two solutions or two unknown function which corresponds to d minus 2d dash, which is sum, which is written here as sum of sum over s x to the power s minus 1 phi r s of minus 2x minus 2y. One can assume instead of phi another function f, where f0 y is phi 0 minus y, and fr minus fr 2x plus y as phi r minus 2x minus 2y. So, this is the general solution of the given equation where the roots are repeated. Till now, we have discussed how to find complementary function when the operator or the function f is given in reducible form. Now, there is another case when f is not reducible or f is in irreducible form. So, for that case, it may not be possible to get a solution containing full number of arbitrary functions, but it is possible to find solutions containing as many arbitrary constants as we desire. To illustrate this idea, we shall take one example. So, to go to the, before going to the example, we need to explain one theorem which is stated here. F operated over e to the power ax plus by is equal to f of ab e to the power ax plus by. The proof of this theorem is very simple, because we know that if we operate a differential operator to an exponential function, then the coefficient of x will come instead of d, and the coefficient of y, that means b, will come instead of d dash. Now, using this theorem, one can see that if the equation is given in the form capital F z equals to 0, we can assume a solution in the form e to the power ax plus by. So, if we apply this function instead of z, we will get, according to this theorem, capital F a b e to the power ax plus by. Now, this e to the power ax plus by will be a solution of the equation f z equals to 0, provided capital F a b equals to 0. So, from the equation f a b equals to 0, one can obtain a set of values for a and b which satisfies this equation. Let those set of values are AR, BR. Now, these are the solution of the given equation. So, their linear combination, that means sum of CR exponential of ARX plus BRY is the solution of the given equation FZ equals to 0, where AR, BR, CR are arbitrary constants and AR, BR satisfies the equation if AR, BR equals to 0. So, in this example, if you see the first factor, this is reducible because the first factor is a linear factor, but the second factor is not reducible. That means that factor cannot be written as the product of two linear factors. So, for that case, we can assume the solution in the form e to the power ARX plus BRY, where AR/BR satisfies the relation AR square plus BR plus 3 equals to 0. And for the reducible factor, the solution is e to the power minus 5x phi of 2x plus y. Therefore, the required solution of the given equation is z equals to the linear combinations of these functions. Here we have to note that there are infinite number of points which satisfies the relation AR square plus BR plus 3 equals to 0. So, the summation, in the summation there are infinite number of terms, there may be infinite number of terms in this summation, but this series should be uniformly convergent. In the last section, we have discussed about the method of finding complementary function of a linear PDE with constant coefficients. Now, we are going to discuss how to find particular integral of a non-homogeneous PDE with constant coefficient. And we shall discuss some particular cases. We shall take the function exponential function, polynomial function, sine or cosine functions and the combination of these functions. Taking this type of function, we shall derive some rules for finding particular integrals. We shall also discuss when the equations are given in the form of Cauchy-Euler form, that means when the coefficients of the differential equations are not constants, but those coefficients are variables, but those variables are in some particular form. To discuss all these, we need to go to the slide show. Suppose we have an equation capital F z equals to small f x y. So, a particular integral can be considered as an operator 1 by f operating on small f, and we shall discuss to find particular integral for some particular cases, that means when small f is some particular functions. First, we shall start taking small f as a polynomial in x and y. So, f x y can be written as sum of a r s x to the power r y to the power s, where r and s are positive integers or 0 and a r s are constants. So, if small f is given in this form, particular integral can be written in this way as 1 by d to the power n small f d dashed by d operating on small f x y, where small f d dashed by d to the power minus 1 to be expanded in binomial theorem, and the highest power of y in f x y be if b m, then we need to retain the terms up to d dashed by d to the power m. The idea will be more clear if we take one example. So, we take this example. So, in this example, small f function is x square plus xy plus y square, and capital F is capital D plus d dash square. So, it is very easy to find the complementary function. So, complementary function is written here. Since there is a repeated root, we will get the complementary function in this form phi 1 x minus y plus x into phi 2 x minus y. Now, particular integral is 1 by capital F d dashed operator. So, in this case it is 1 by d plus d dash square operating on x square plus xy plus y square. Now, here we take the factor d square and then the denominator becomes 1 plus d dashed by d to the power 2. So, we need to operate 1 plus d dashed by d to the power minus 1, and we have to expand this series in binomial. So, the binomial expansion of that operator becomes 1 minus 2 d dash by d plus 3 d dash square by d square minus dot dot. This binomial series contains infinite number of terms, but since in small f, that means in the function x square plus xy plus y square, the highest order of the polynomial is 2, then it is sufficient to take the terms up to d dash square by d square. So, that is why we took only the first 3 terms in the expansion. So, in the second line we write, we first operate 1 on the function x square plus xy plus y square. So, it becomes x square plus xy plus y square, and if we operate the second term minus 2 d dash by d, this d dash is the differential operator with respect to y. So, if we differentiate x square plus xy plus y square with respect to y, it becomes x plus 2y, and now if we operate the third operator 3 d dash square by d square, that means d dash is the derivative with respect to y. So, d dash square represent derivative with respect to y twice. So, if we take second order derivative of x square plus xy plus y square twice with respect to y, it becomes y. So, the terms becomes 1 by the second line, it is written in the second line, 1 by d square x square plus xy plus y square minus 2 by d x plus 2y plus 3 by d square into 2. Now, you have to remember that d represent the differential operator with respect to x. Therefore, 1 by d represent the integration with respect to x. So, 1 by d square is nothing but twice integration of the function x square plus xy plus y square with respect to x. So, this gives the term x to the power 4 by 12 plus x cube y by 6 plus x square y square by 2. Now, come to the second term, 2 by d operating on x plus 2y, that means you have to operate 2 by d cube on the term x plus 2y. So, it gives minus 2 into x to the power 4 by 24 plus x cube y by 3, and the last terms gives the fourth time integration on the function 2. So, it is nothing but integration of 1 with respect to x. So, it gives x to the power 4 by 24. So, after simplification it becomes 1 by 4 x to the power 4 minus 2 x cube y plus 2 x square y square. So, the required solution or the general solution of the given equation is the complementary function plus particular integral. So, it is z equals to phi 1 plus x phi 2 plus 1 by 4 x to the power 4 minus 2 x cube y plus 2 x square y square. Now, I am going to discuss the case when small fy is in exponential form. So, the particular integral can be written as 1 by fd operating on e to the power x plus by. So, 1 by fd can be considered as the inverse operator of the operator capital F. So, we know the property of exponential function. So, using that property we can write the particular integral as 1 by f a b e to the power into e to the power ax plus by, provided capital F a b is not equals to 0. And the case when f a b equals to 0, we shall discuss that case separately. Now, take this example. So, in this example we can see that it is in the complementary function it is reducible to linear factor. So, it is easy to find the complementary function which is linear combination of phi 1, phi 2, phi 3, where phi 1 is function of y minus x, phi 2 is function of y plus 3x, and phi 3 is function of y minus 2x. So, particular integral is 1 by f d operating on e to the power 2x plus y. So, if we use the rule which is written in B, we need to replace d by the coefficient of x, that means 2, and d dashed by coefficient of y, in this case it is 1. So, it becomes 1 by 2 plus 1, 2 minus 3 into 2 plus 2 into e to the power 2x plus y. So, minus 1 by 12 e to the power 2x plus y. The general solution becomes z equals to phi 1 plus phi 2 plus phi 3 minus 1 by 12 e to the power 2x plus y, that is complementary function plus particular integral. Now, I am going to discuss the case when small f is either a cosine function or sine function. First of all, we shall discuss when capital F is in the form of, which is written here, phi of d square dd dash d dash square. That means the function f is some function of d square d dash or d dash square. So, for that case, if we operate phi on the function cos x plus by, d square will be replaced by minus a square and dd dash will be replaced by minus ab and d dash square will be replaced by minus b dash square. So, using this property, one can find particular integral in this form. So, particular integral is 1 by f operating on cos x plus by. So, this equals to 1 by phi operating on cos x plus by. So, that equals to 1 by phi minus a square minus ab minus b square cos x plus by, provided phi minus a square minus b square minus b square is not equals to 0. The same rule is applicable when there is sine function instead of cos function. So, here is one example. The right hand side is sin x into cos 2x. So, to apply the previous rule, we need to write this function as in this form, sine of x plus 2y minus sine of x minus 2y. So, complementary function is very easy to find. So, complementary function becomes phi 1 y plus phi 2 x plus y, and the particular integral is half of 1 by operating on d square minus dd dash on sine x plus 2y. So, according to previous rule, we need to replace d square by minus 1 square and dd dash by minus 1 into 2. So, that rule is applied here, and for the second function we are using the same rule and getting the particular integral as half of sine x plus 2y plus 1 by 6 sine x minus 2y. Thus, the required solution becomes z equals to Cf plus Pi. Now, I am going to discuss the case where capital F A B equals to 0. So, if capital F A B becomes 0, then the earlier methods will not be applicable. So, for that case, in the function capital F d d dash, there will be a factor b d minus a d dash. So, we can take out that factor from f, and the f can be written as b d minus a d dash into some g of function which is function of d and d dash, and we also assume that g a b is not equals to 0. Now, consider the differential equation b d minus a d dash z equals to capital F a x plus b y. Now, the corresponding subsidiary equation, this is a first order partial differential equation. So, we can write the corresponding Lagrange equation, which is written here dx by b equals to dy by minus a equals to dz by f of ax plus by. Taking first two equation, one can obtain a solution as ax plus by equals to constant. Let that constant is c. Now, taking the first and third equation and using the relation ax plus by equals to c, we get the equation dx by b equals to dz by fc, and solving this equation we get z equals to x by b into fc. Now, we replace c by the function ax plus by, we get z equals to x by b into f ax plus by. So, the particular integral for this equation can be written as z equals to 1 by bd minus a d dash operating on f is equal to x by b f ax plus by. Now, we shall use this concept to solve the equation where f a b equals to 0. Now, think about the equation where f a b equals to 0. For that case, particular integral is 1 by f operating on small f. Now, capital F can be written as bd minus a d dash into g capital G d d dash. Since capital G a b is not equals to 0, after operating 1 by capital G d d dash on f ax plus by, one can replace in the function g d by a and d dash by b. So, we obtain the expression 1 by g a b into 1 by b d minus a d dash operating on small f. And now, we need to apply the previous concept where we obtain the solution of b d minus a d dash z equals to f. Using that concept, we can write this expression as x by b into f ax plus by. So, the particular integral for this case becomes x by b g a b into f ax plus by. Now, think about the expression for capital F, which is b d minus a d dash into g. Now, if we differentiate the function f with respect to d, we get f dash d d dash equals to b g plus b d minus a d dash into g dash. So, f dash a b is equal to b into g a b. So, particular integral becomes x by f dash a b into f ax plus by. So, here b into g is replaced by f dash, provided f dash a b is not equals to 0. Now, we shall illustrate that idea using this example. So, this is a second order linear partial differential equation with constant coefficient, but the right hand side is some function of x plus 2y. So, in this case we can see that complementary function, since there is a repeated root in capital F. So, complementary function can be written in this way: phi 1 x plus 2y plus x phi 2 x plus 2y. Now, the particular integral, it becomes 1 by f d square 4 d square minus 4 d d dash plus d dash square operating on 16 log x plus 2y. And just before we have learned that this becomes 0. So, a particular integral can be written as x by f dash a b into small a x plus b y. So, we use that concept. So, it becomes 1 divided by f dash. So, it is 8d minus 4d dash operating on log x plus 2y. Again the denominator vanishes for d equals to 1 and d dash equals to 2. So, it again becomes x divided by f dash. So, in this case f function is 8d minus 4d dash. So, its derivative with respect to d is only 8. So, particular integral is 16 x square divided by 8 into log x plus 2y. So, after simplification it becomes 2 x square into log x plus 2y. Now, f may be combination of exponential function and the another function. So, it can be written as e to the power ax plus by into v. So, for that case particular integral can be written as 1 by capital F operating on e to the power x plus by into v, and e to the power x plus by can be taken out from the operator 1 by v, 1 by f, and in the function f d will be replaced by d plus a and d dash will be replaced by d dash b, and that will be operated on the function capital V. Now, I want to discuss about a particular form of a second order differential equation where the coefficients are not constant, but the variable coefficients. But these variable coefficients has some particular form, that means capital F, the function capital F can be written as function of x into capital D and y into d dash. So, if the capital F is in this particular form, that equation is known as Cauchy-Euler equation. Though the Cauchy-Euler equation is a differential equation with coefficient are not constant, but this equation can be transformed into an equation with constant coefficient with some transformation in the independent variables x and y, and the transformation is this: x equals to e to the power u and y is equal to e to the power v. So, if we write down the equation, the given equation in terms of the variables u and v instead of x and y, the equation will become a differential equation with constant coefficients, and we know how to find the solution of a equation with constant coefficients. So, using those concepts, one can solve this particular type of equation or the Cauchy-Euler equation using this transformation. Thus, in module 2 of chapter 3, we have learned how to find complementary function of a partial differential equation with constant coefficient, and we have learned how to find particular integral of that equation taking some particular functions such as exponential function, polynomial function, sine and cosine function, and the combination of these functions. We have also discussed how to find solution of a equation when the equation is given in Cauchy-Euler form. So, in this way we end this module.